favorite problem in AP Chemistry is where you are given information about a combustion reaction and we need to use that information to determine the empirical formula of the compound. So let's refresh ourselves first on what is combustion. Well, remember, chemists view hydrocarbons as combustible. So that's our fuel for burning. A hydrocarbon is a compound mainly composed of carbon and hydrogen, but of course you can have other elements like oxygen, nitrogen, sulfur. And of course, we need oxygen to accomplish the burn. And we know if it's complete combustion that we will definitely get some carbon dioxide, some water, and then depending upon what these other elements are, we may get other products. But the understanding is this. All of the carbon that is in the hydrocarbon will go towards the amount of carbon dioxide, and all of the hydrogen will then be used to form water. And so if we can measure the amount of carbon dioxide, measure the amount of water, use these to find out the grams or the moles of carbon, the grams or the moles of hydrogen, well then we can kind of back calculate to ultimately determine the empirical formula of our compound. All right, so let's dig into our example. To give a good image of the setup, imagine if you would place your compound that you're trying to find the empirical formula of in this reaction chamber, and then of course you flood it with oxygen and then provide some kind of a spark. Well, we know again that carbon dioxide, water, and maybe some other products will come out. And so we're going to push those product gases and then have materials that can absorb the water that is produced and then absorb the carbon dioxide. Now they could be in different orders. And if we know the mass change of these, we can find the amount of water that was produced, the amount of carbon dioxide that was produced. Knowing the amount of this that we reacted, we can find out our empirical formula. So let's dig into this example. All right, we are trying to find the compound, and we're told right off the bat it's made of carbon, hydrogen, and nitrogen. And we want to find out our subscripts. So I'm just going to call them X, Y, and Z for now. We are combusting 35 milligrams of it. I'm going to go ahead and divide that by 1,000, so I know it'll be 0.0350 grams, respecting sig figs. Now, combustion, I know, is reaction with oxygen. And I know I'm going to produce at least carbon dioxide and water and maybe some other things. Well, I don't know the formula of this, so there is no way I could balance this equation. And that is okay that I don't know my other products because I'm not trying to do stoichiometry here. I know that all the carbon that was here can be trusted to go here. And all the hydrogen can be trusted to have gone there. And I'm told that I made 33.5 milligrams of carbon dioxide and 41.1 milligrams of water. Going ahead and converting these to grams, dividing each by 1,000, 0.0335 grams, 0.0411 grams of water. Okay. Now, empirical formula, I want to know how many atoms of each element are there per ratio of each other, but I also know if I can find the mole ratio. So that is what I'm ultimately trying to find. So if I start out with 0.0335 grams of carbon dioxide and 0.0411 grams of water, can I then, using dimensional analysis, convert to just grams of carbon and moles of carbon? And of course I can. And then the same for grams of hydrogen and moles of hydrogen. So digging in, taking one step at a time. Formula mass of carbon dioxide, 44.01 grams in every 1 mole. And then my gut is to go right then to moles of carbon. So I'm just going to interpret my formula correctly, for every 1 mole of CO2, I have 1 mole of carbon. And sig figs, I get 0.000761. Please feel free to convert that or translate that into scientific notation. And then I can get grams by just using average atomic mass. Okay, so I know my moles of carbon, and I know I'm going to need that for empirical formula, and my grams of carbon. I'll go ahead and do that for my water as well, very, very quickly. Formula mass. Now be so careful. This is the main place that students make a misstep. There's 2 moles of hydrogen for every 1 mole of H2O. And then that gives me moles of hydrogen, 0.0456. And then getting grams. All right. Now, how do I find out nitrogen? Well, all the carbon went here, all the hydrogen went there. So if I take the mass of my compound and then subtract from that the mass of carbon and the mass of hydrogen, well, then I'll have my mass of nitrogen, which with sig figs, 0.0212. And then, of course, getting that 2 moles. And this is 0.00151 moles of nitrogen. Sorry, I'm going so quickly that it's a little sloppy. Okay, so I have moles of each. And I know then that, and this is a little neater, that if I go ahead and look at my moles of carbon, hydrogen, and nitrogen, and I lay them out here because this is just more clear for whoever's looking at my work instead of trying to do my next step here. I know that I choose my smallest number, which is my moles of carbon, divide each by that, and then I get this beautiful whole number ratio, and there's my empirical formula. So this is kind of an indirect way to use our understanding of the relationship of grams and moles and law of conservation of mass. All the carbon that's here is going there and so on. I know how to find an empirical formula to go ahead and find that. And there is an additional problem here with the correct answer. I encourage you to try that. These are really, really fun problems. Make sure you're trusting your talents and your abilities. You're just taking one step at a time, remembering innately how do we use moles of each element to get our empirical formula.